Hello everyone and welcome to lecture. Today's lecture will be on the multivariate chain rule, and we're going to go through and essentially see how to generalize the chain rule from single variable calculus to multivariable calculus. And essentially this is going to answer the question of how do we differentiate or take the derivative of a multivariable composition of functions. Because it turns out that when you start dealing with compositions of multivariable functions, you can run into very, very complicated chains of dependence, or the total dependence of one function on a number of other functions could be very, very, very complicated. So that the multivariable chain rule answers the question of how do we do this correctly. So we'll start by reviewing the simplest possible chain of functions, which is just a single dimensional chain. So you'll remember from your 1D calculus class that a 1D chain of functions, or composition of functions, is the simplest possible chain. So let's suppose we have that W is the output of one function, which is a function of some variable U. And we'll also suppose that U is equal to some other function, G of X. So we visualize this dependency, this chain of dependence, using what's called a tree diagram. Okay, this tree diagram kind of gives us a visual aid in looking at this chain of dependence. Specifically, the tree diagram for this scenario is going to look like the following. You're going to have that W depends on U. So we draw a line from W to U. And then U depends on X. And we label the edges of the tree diagram with exactly how the top variable, or the variable above, depends on the variable immediately below it. Specifically, the rate of change of W with respect to X is going to be the derivative of the function f with respect to U, or f prime of U. And similarly, the rate of change of U with respect to X is going to also be written on this label right here, because this line represents that U depends on X. So the rate of change of U with respect to X, or G prime of X, is what this line gets labeled as. And so we know then that if you want to figure out the rate of change of W with respect to X, the top variable with respect to the bottom variable, or dW dx, that amounts to taking the x derivative of the composition f of g of x which in your single variable calculus class you hopefully saw this is calculated directly using the chain rule. It's the derivative of f at g of x multiplied by the derivative of the inner function g of x, the g prime of x. And this is the multivariable chain rule. This is how we take the derivative along a chain of dependence like this. So this is the same thing as, you can write it in slightly nicer, shorter notation as just df du, or the derivative of the function f with respect to u times du dx, or the derivative of u with respect to x. So either of these two notations are fine to write. Be careful you don't confuse this, though. There's nothing algebraic about this expression right here. This is specifically just stating that the u derivative of f times the u, or the x derivative of u, is in fact equal to the derivative of the upper variable with respect to x. But this notation is going to be helpful to us in terms of, when we go to multivariable functions, because it's going to help us sort of simplify in some sense and write down the chain rule for more complicated compositions in a nicer manner. Just see one example of this. Hopefully you'll remember from a calculus 1 class. But let's say that f of u is equal to sine of u, and u is equal to x cubed. So the composition, or so this is our g of u, or g of x. So w is in fact equal to the composition f of g of x, or sine of x cubed. And if you want to figure out the derivative of w with respect to x, you can do so using the chain rule, which is going to be the derivative of f at g of x times the derivative of g so dw dx is going to be equal to the derivative of sine, which is cosine, at g of x, so it's at x cubed, times the derivative of g, which is going to be 3x squared from the power rule. So this is the correct way of using the single variable chain rule. So this is what we'll be generalizing in this lecture to many different complicated scenarios, and we'll also see how this applies in certain real-world examples. So the next possible, let's say the next possible, simplest case that we consider is if you have the w is equal to a multivariable function of a certain number of variables, and each one of those variables depends on a single value. So each one of those variables is a single function. So we'll say that the next simplest case is a multivariable function of n variables where each of the variables is a single variable function. So we'll consider what this looks like for functions of 2 variables and 3 variables, but the idea is that this extends in general for any number of variables as well. So in the 2D case, we have that W, say, the output, is a function of 2 variables, where each of the inputs to W is itself a function of some, we'll say, some value t, some single variable t. So x equals some function of t, and y is also some function of t. So the tree diagram for this scenario is given by the following. We have at the top, W is the final output of this function, but because W is a multivariable function, it itself depends on two things. It depends on x and y. And each one of these values, x and y, also depend on t. So you see that the chain of dependence, or the tree diagram for this scenario, is a little bit more complicated. Because if you ask, how does W depend on t, or what is the rate of change of W with respect to t, you'll notice that there are two separate ways that W depends on t. If you change t by a small amount, x is going to change, and therefore W is going to change. But if you change t by a small amount, then y is also going to change, which means W is going to change. So there's actually two separate pieces here to this chain that we have to factor in when we look for the full rate of change of W with respect to t. So just like before, we can label the tree diagram, and we label it with, it'll be now the partial derivatives. So the W depends on x through the partial derivative of the function f with respect to x. This is the rate of change of W with respect to x. W depends on y with respect to, the total amount of the rate of change of W with respect to y is the partial derivative of f with respect to y. And likewise, we have here that x depends on t. So this edge right here is going to be labeled as the derivative of x with respect to t, and y also depends on t. So this edge right here is going to be labeled as dy dt. And you'll notice that in order to calculate the full rate of change of W with respect to t, we have to factor in both of these paths right here, because any change in t will result in a change in W through both these paths. And this is the first time that we'll see the full multivariable chain rule. So we can go through and show that the total rate of change of W with respect to t is actually going to be the sum of the normal derivative along each one of these chains of dependence, or each one of these single variable change, single dimensional chains. So the rate of change along this path will be calculated using the single variable derivative. It's just df dx times dx dt, and we have to add to that df dy times dy dt. And there you have it. This is how you do the multivariable chain rule for this tree diagram, this chain of dependence. In general, this is going to be how we always go through and do the multivariable chain rule. Now, it's interesting to note here that this has actually a lot of geometric significance, and we'll see that if we introduce the dot product between vectors. So this expression right here is the same thing as dw dy, dw dx, comma dw dy, dot product with the vector x prime y prime. You'll remember from a previous calc course that the dot product between vectors, if I have a vector A and a vector B, the dot product between vectors A dot B is just the sum of the multiplication of each individual component. So A1 B1 plus A2 B2. That's how you do it for a vector with two components. But this vector isn't just any old vector. It's a very special vector. What we've shown is that dw dt is the gradient vector, or this is the gradient vector, and it's the vector dot product with this x prime y prime, which is sometimes called the velocity vector along a given curve. So what we've stumbled upon, and this also holds in 3D as well, I'll go over how this is in 3D in 1 second, but if we kind of graph out here what's going on, this is the x-axis, the y-axis, and we have some function f of xy with level curves. Say maybe the level curves look like this. So if you look at r of t is x of t so if you say x is a function of t and y is a function of t, you have an expression for what's called a parametric curve. You should see this, you should remember this hopefully from a previous calculus course. So whenever you have the x coordinate and the y coordinate are a function of a single parameter, you have a parametric curve that's essentially giving you a point on a curve at a whole bunch of different points at any given t value you might choose. So what we've just figured out using the multivariable chain rule is how to take the derivative along a curve. It's saying that the derivative, or the rate of change of any function along a curve, is the gradient of that function dot product with the velocity vector along the curve. The velocity vector v is always tangent to the curve at any given point. So if f, say, is a temperature function, then this quantity that you calculate is the rate of change of temperature along a curve as you're traveling in a certain velocity. So this also works in 3D as well. Even the curve interpretation works in 3D, which is very cool. So in 3D, this is the scenario where W, the output, is a function of 3 variables. And each component, x, y, and z, are all a function of a single variable that we'll call t. the tree diagram for this scenario. Gives us that W depends on X, Y, and Z. And each of these values, X, Y, and Z, all depend on T. So from the multivariable chain rule, if you want to figure out dw dt, this is going to be the partial derivative of w with respect to x times dx dt plus the partial derivative of w with respect to y times dy dt plus the partial derivative of w with respect to z times dz dt, which is the same thing, just like before, as the gradient vector of the function f, and then dot product with the vector v, where this is the velocity vector of a curve in 3D. So again, if you have some path, say, some particle maybe that's moving along this path that you call r of t, the velocity vector of this curve is always going to be tangent to the curve, and the derivative of r of t. And we're seeing that we just showed that the from the chain rule, the multivariable chain rule, the rate of change of w along the curve is the gradient of the function f dotted with the velocity vector. This is a really cool thing here that we're kind of discovering, that this allows us to really accurately describe the rate of change of functions along curves, and we'll actually see that this also allows us to describe the rate of change of multivariable functions on surfaces, or with any possible geometric object that we might want to consider the rate of change of a function on. Remember that this was calculated directly, using single variable chains, because along each of these branches, right, this branch right here, the rate of change represents the rate of change of w with respect to x. This middle branch represents the rate of change of w with respect to y. This branch right here represents the rate of change of w with respect to z. And this branch represents dx dt. This branch represents dy dt. And this branch represents dz dt. So we'll look at a specific example in 2D to kind of see how we can go through and do these calculations and use what we've just shown. So let's see an example of this in action. What we'll do is consider the problem of solving for the rate of change sometimes we'll just abbreviate this by ROC of the temperature function, where W is the temperature, and we'll say that W is given by the function x squared minus y squared. Along the curve generated by an ellipse. Or an elliptical level curve. So, and we'll use a specific ellipse. We'll use the ellipse with the semi-major axis along the x-axis of length 2, and the semi-minor axis along the y-axis of length 1. So this is the algebraic equation of an ellipse with those parameters. And specifically, we'll look at this at a specific point. We'll say, look at the rate of change of temperature along the curve generated by an ellipse. At the point R naught is equal to 2 over the square root of 2 for the x component and 1 over the square root of 2 for the y component, using the standard parameterization of the ellipse. So first things first, let's kind of get a picture of what this looks like. And also remember the standard parameterization of the ellipse. So just like the circle, for any ellipse, right, the equation is going to be x over a squared plus y over b squared is equal to 1. This is an ellipse that stretches along the x-axis at length 2a and the y-axis of a length 2b. And for any ellipse, we can parameterize that ellipse by the following. We say that x of t is equal to a times cosine of t, and y of t is equal to b times sine of t for t between 0 and 2 pi, where t is representing the angle that we're looking at. So this is the standard way of parameterizing an ellipse, and this is what we mean by the standard parameterization of the ellipse. So we want to figure out at this exact point on the ellipse what exactly the rate of change of the function x squared minus y squared is along the ellipse. So we also want to get an idea of what this is looking like when we try and get a picture of this function. And we can do this very, very nicely using the level curves of this function. So we have an x-axis here, a y-axis. You'll remember that the level curves of this function, the function x squared minus y squared, look like the following curves. When the function is equal to 0, you get two straight lines, y equals x and y equals negative x, for the level curves of the function. This corresponds to w is fixed at 0. And then for other values of the function, you get hyperbolas. So say when w is equal to the fixed value of positive 1, say, you get a hyperbola that maybe intersects. I'm going to do two intersections right here and right here as well for negative 1. So when w is equal to positive 1, you get a hyperbola that looks like this right here. This corresponds to a fixed value of w is equal to 1. You also have a hyperbola goes right here as well. corresponds to w is equal to 1. And when w is equal to 2, you get a similar. We'll just say, actually, we'll call this one, though, when w is equal to 4. Same thing here as well. And then as w increases, you get hyperbolas that are further and further and further out. And you get the same sort of picture when you have considered negative values of w, when w is negative. I'll do the negative values of w as a dotted line right here for this hyperbola. And this corresponds to w is equal to negative 1. Same thing right here. So this value corresponds to w equals negative 4. So there you have it. This is what the level curves of this function look like. And then along the ellipse of semi-major axis along x of distance 2 and semi-minor axis of distance 1, this right here is exactly that curve. So this is the curve C that we're looking for the rate of change of the function along. And specifically, right, you can actually do this for any point, but we're looking directly for the rate of change of this function at the point 2 over square root of 2, 1 over square root of 2, which is definitely a point on this ellipse. So it's going to be at an angle of 3 pi over 4. So this is the specific point that we're looking at. This is our value R0. So what we're looking for is the rate of change of the function with respect to the standard parameterization tangent to the curve right here at this point. So we have our parameterization, we have x of t, y of t, and we also have a chain of dependence, or a tree diagram, that directly describes everything we need to know to take this partial derivative. Or actually, it's a total derivative. Specifically, the temperature, W, is a function of x and y. And on the ellipse, when you're kind of going around the ellipse in this parameterization, x and y also depend on t, the parameter of the curve. So that tells us that from the multivariable chain rule, the rate of change of temperature with respect to the parameter t is going to be equal to the sum of df partial f partial x times dx dt, or x prime, plus partial f partial y times y prime, because this term is the rate of change of f with respect to y. This term is the rate of change of y with respect to t. And the idea is that we're really only trying to evaluate this at one fixed point, at the point R naught. Right, so we'll make a point to write that down. We're going to be essentially evaluating this entire thing at the point R naught, at one fixed point. Same thing right here. So you got to figure out what this is at the point of evaluation. Now this process that we're doing holds for any point on this curve, but we're really, in this problem, only just looking at one fixed point. But before we plug into that point, we want to go through and do our calculations. So df dx at R naught, well, if f is the function, f of xy, remember, is x squared minus y squared, df dx is the derivative of that with respect to x, the partial derivative, so it'll be 2x evaluated at R naught. This will be multiplied by x prime, and remember, so if this is our general parameterization for the ellipse, this curve C, right, our blue curve right here, is the ellipse with a equals 2 and b equals 1. So it's x of t is equal to two times cosine t, and y of t is equal to just sine of t. So that means that x prime, or the derivative of x of t, is going to be negative 2 times sine of t. Again, this is evaluated at that point R naught, plus df dy, which is negative 2y evaluated at the point R naught, times the derivative of sine of t, y prime, which is going to be cosine of t at R naught. And you could go through and show directly that this angle, right, this angle t at this point right here is, so t at that point, or t naught, is equal to 3 pi over 4. It's going to change depending on what point you choose. So you could just plug in 3 pi over 4 here for t and be done with it. But I'll show you how you can also do the following. You can use the fact that for any value on the curve, x is equal to 2 cosine of t. So cosine of t is the same thing as x over 2 for points on the curve for any angle on this ellipse. And same thing, because y is equal to sine of t, well, that means that whenever you see a sine of t, you can replace it with the y value for the point on the ellipse, which is nice. And what you end up getting here when you plug in is you're going to have 2 times x, and the point x at R naught is 2 over the square root of 2. So it's going to be this times negative 2 times sine of t, which is negative 2 times 1 over the square root of 2, because sine of t is just equal to y on this ellipse. And this is going to be plus negative 2 times y, which is 1 over the square root of 2, times cosine of t, which is x over 2. So this x over 2 is 2 over the square root of 2 over 2. And we can simplify this a lot. Specifically, you have here 2 over the square root of 2. You have this 2 right here over 2, so these two 2's cancel out. You're going to end up getting and I think I missed, there should be a negative sign right here because this is the x coordinate. We should also have a negative sign right here as well because that was our x coordinate. So this entire thing simplifies to 4. The negative signs cancel one another. It's 4 times square root of 2 times 1 over the square root of 2 plus this is going to be 2 over the square root of 2 is just the square root of 2 times 1 over the square root of 2. So the square root of 2's cancel out in both cases, and you're left with just 4 plus 1, or 5. So this is telling us that this is the rate of change of the temperature function, the specific temperature function at this point with respect to the standard parameterization of the ellipse. So if you're moving around the ellipse, say, according to the standard parameterization, this is what you feel in terms of the temperature. You're seeing that it depends both on the speed at which you go around the ellipse and the function itself. So the units of this would be, say, if you're measuring in degrees Fahrenheit, the units would be degrees Fahrenheit per second, say, if t is a time in terms of seconds. But the units could depend on what the problem and what units of measuring you're using to measure your answer. Now you'll notice that this actually makes a lot of sense if you look at the actual point itself, right? If you look in the direction tangent to the curve going around the ellipse in this direction with respect to the x-axis, you see that in that direction the function's moving up. Your level curves are increasing, so you expect to get a positive value for your rate of change. And this is directly matching. So this is directly matching exactly what you would expect from this plot of the level curves of the function. The level curves aren't going to give you the exact value of the rate of change at any point. You can only do that using this exact, the exact computational method. But the level curves can help you verify your result to sort of check your work and make sure you're doing everything. What the picture of what the function should be doing is matching up with what you're doing in terms of your calculations. So we've seen the simplest form of the chain rule, the multivariable chain rule, and it definitely does get a little bit more complicated as we kind of introduce more and more multivariable dependencies. So the next step is going to be considering a multivariable function that depends on more multivariable functions. So the next multivariable chain rule to consider is a multivariable function that depends on more multivariable function. You could say several other. So we'll just say several other multivariable functions. And again, just like the other examples, you can do this in 2D, 3D, any number of variables, but we'll start by just considering the 2D case, where w is some function, the multivariable function, say f of x, y, and we'll say that x is some function, we'll say g of uv, and y is some function h of uv. And the tree diagram for this scenario becomes a little bit more complicated. Okay, this tree diagram for this chain of dependence is going to be that w depends directly on x and y, which both depend on u and v through the functions g and h. So you'll see from this why we call a tree diagram a tree diagram. You know, depending on how complicated the multivariable expression is that you're looking at, right, this is what we have for our tree diagram. So it's kind of rooting and becoming more and more complicated the more and more interdependencies we have. The labels that we put on the tree diagram are still the same, though. This branch right here is going to stand for df dy, the partial derivative of f with respect to y. This branch is going to correspond to df dx. This branch right here is going to correspond to dg du, or partial g, partial u. These are all partial derivatives now because we have all multivariable functions. This branch is going to correspond to df, or dg dv. This branch right here corresponds to partial h, partial v, and this branch right here corresponds to partial h, partial u. And now we could ask the following two questions. What is the rate of change of w with respect to u? And what is the rate of change of w with respect to v? Because now w depends on two things. It depends on both u and v. Specifically, it depends on u through this path right here and through this path right here. And it depends on v through this path right here and this path right here. But what's nice is that if you understood the previous multivariable chain rule, so the multivariable chain rule where you have a multivariable function and a whole bunch of single variable functions, the algorithm for going through and getting the correct partial derivative is the same. Right? So when we're looking for the partial derivative of w with dw du, we have to ask ourselves how many different ways does w depend on u, and directly it depends on u through this path right here, and it also depends on u through this path right here. So we apply the single variable chain rule along each of these paths, and we just add the answer together. It's the correct way of doing the multivariable chain rule for this tree diagram. So you can see very clearly that the tree diagram is directly, it's extremely important in calculating the chain rule correctly. So dw du, the partial derivative of w with respect to u for this tree diagram is going to be the partial derivative of f with respect to x times the partial derivative of g with respect to u plus the partial derivative of f with respect to y times the partial derivative of g, or of h with respect to u. And just like before, we can simplify this a little bit. You can write this as df dx df dy is just the gradient vector. So it's the same thing as the gradient vector of the function f at a point. And it's the dot product, the vector dot product, with what we call the partial derivative of the position vector with respect to u. Where the position vector, remember, we can call it it's xy, and both x and y are functions of u and v. So the x is g of uv, and y is h of uv. This would be a more simplified way of writing this expression right here. Similarly, for the partial derivative of w with respect to v, w depends on v along this path right here and along this path right here. And I'll underline the red and the blue from before just so that you can kind of see and remember how we're calculating this. We have to sum all possible paths of dependence. So dw dv is going to be df dx times dg dv plus df dy times dh dv, which again is the same thing as the gradient of the function f dot product with dr dv. So this would be the general way in 2D of computing the partial derivative if you have this chain of dependency. You could have a similar scenario in 3D. Where you have, say, a function of 3 variables, so w is equal to a function of x, y, and z, where each one of these is a function of 2 variables, so x, say, is equal to f of uv. And instead of using instead of using different functions, let's just say x is equal to some function of u and v, y is equal to some function of u and v, and z is equal to some function of u and v. So the tree diagram for this scenario would be that f depends on x, y, and z. Let's make this a little bit bigger. So f depends on x, y, and z. And if each of these is a function of 2 variables, u and v, and you have that x depends on u and v, y depends on u and v, and z depends on u and v. The z depends on u, and it depends on v. This would be the correct tree diagram for this scenario. And if you want, you can go through and put in those labels just like before. And in the slides, my lecture slides, I have the labels put in as well. But the idea is that if you want to figure out, say, the dependence of w, and we'll put w here too, because w is what we're using for our ultimate dependent variable. dw du is going to be equal to all paths of dependency. So there are w depends on u through x, w depends on u through y. So through this path right here. And w depends on u through z. So there's going to be 3 terms, the sum of 3 terms. Dependence of w on u with respect to x is going to be df dx times dx du. That's this red dependence right here. Df, next term is going to be df dy times dy du plus, that's the blue dependence, plus df dz times dz du, or partial z partial u, which again is now the gradient vector in 3D, dot product with dr du, where r here now is a vector in 3D, each of which the components are functions of u and v. You can go through and do the same thing for dw dv. Look at that, dw dv is the gradient of the function f, dot product with dr dv, or partial r partial v. So this is a very, very powerful method. You know, you can even do this if you have a function of 3 variables of another function of 3 variables. This would end up working out. So I encourage you to do that. You know, it's a good idea to go through, and it's definitely in the slides that I'll post. But if you have, say, that w is equal to a function of x, y, z, and x is a function of, we'll say, maybe it's a function of r, s, and t. Y is a function of r, s, and t. And z is a function of r, s, and t. I encourage you to go through and draw the tree diagram for that, and then figure out what the correct partial derivative should be for this scenario. It'd be a good exercise. But this, by the way, if you want a kind of a geometric interpretation here, whenever you have the x coordinate, the y coordinate, and the z coordinate are given by 2 parameters, you have what's called a parametric surface. Just like before, we have in 2D or in 3D as well, if they're all functions of a single variable, you have a parametric curve. This is what's called a parametric surface. So very often what we can do is describe a surface in terms of what's called a parametric surface, where points on the surface, on the, maybe it's a level surface, are given by the position vector, the x, y, and z coordinate, as a function of the parameters of the surface. So it turns out that this is a way of figuring out the derivative of a function of 3 variables on a surface, similar to how before, the previous example, we were able to solve for the rate of change of a function on a curve. So this is definitely a very, very powerful technique that we'll learn how to use as we kind of go forward and see more examples. That will conclude today's lecture. Thank you very much for listening, and I hope you learned something and had a great day.